Multiple subplots. So sometimes it is helpful to compare different views of data side by side. Uh, so to this end, Matplotlib library has the concept of subplots for grouping smaller axes that can exist together within a single figure. So before going to that, let's see what is multiple plotting. And I'm going to show you one example using the NumPy and Matplotlib library. And here in this, you will find two plottings in one picture or in one output. So a plot with too much data can be difficult to read. So furthermore, if different data series in a plot have different ranges of values, then interpreting the data becomes impossible. So let's consider the program as shown that plots two data series. Here, let's go through the code. First, importing the NumPy, then importing the matplotlib pyplot, and two temporary names are being used for NumPy NP and for matplotlib pyplot PLT. And then we are using three web parameters for. So here we are trying to make an attempt to plot a 3 hertz sine wave. The frequency is 3 and an amplitude spectrum of first Fourier transform of the wave. And here, however, the plot does not convey much useful information because our axis will be automatically scaled to fit the larger FFT result values, making the sine wave in blue difficult to see. So before going to that, let's see what are our variables we are going to use. So frequency 3, sampling rate of the wave is 100, and the time step, which is nothing but your interval, and it is determined by 1.0 divided by the sampling rate, that is 100. So these are the three parameters we are going to use as the plotting variables in two plots through one picture or one figure. So let's review our parameters. Mm, okay, so like our range function, we are going to use the arrange function of the NumPy library. And here it will return an array with evenly spaced elements starting with this value 0.0 and stopping with 5.0 and with an interval of time step which is calculated here. Okay, so let's see what value will be printed. What value we are supposed to use in T1 here. I'm just going to run the code. Okay, we can see it later. Yeah, so these are the values starting with 0.0 and ending at 5.0, and these are the value we will be using for our plotting. I'm just going to comment it out. I just want to show you what values we will be using. Then one sine wave is to be computed. So using the NumPy library through this statement here, the wave parameter is to be determined using the sine function of the NumPy library using this argument. So it will return a sine value of the wave for this past argument, which is frequency 3 multiplied by 2 multiplied by np dot pi, which will be the by default value 3.14, and t1, all these values. Okay, so let's see what do we have here in wave argument. Just wanted to see what value we will be using in the plotting. There are so many lines, it just squeezed all of them. Yeah, so here are the values for the wave we are going to use in our plotting. Going to comment it out. Okay, now next FFT result. So here I'm going to use one first Fourier transform, one FFT function. Okay, which belong to the NumPy library, and it will return one dimensional discrete first Fourier transform value corresponding this wave arguments or wave values. So let's just see or just review what values we are going to use. Okay, the result. Well, so let's see. I'm just going to run the code. Yeah, so here are the values we will be using in our plotting. So this is one argument, F50 result, trying to comment it out for not executing it. And then T2, another argument using the F50 frequency of the NumPy library, using the length of T1 and the time step that is from here. We are going to calculate the frequency means for the first Fourier transform parameters. Just trying to print it out to see what values we need. Okay, so here are the values parameters for T2 as you see. Okay, so we went through all the values that we will be using in our plotting. So here we are supposed to use this T1 and web parameter values in one plotting, and T2 and NP absolute using the absolute function of the NumPy library. All the absolute values of the F50 result will be taken into consideration in the plotting. I'm just trying to show them together. So let me just run and see what plotting are we going to retrieve from this. So here see we have two plotting options, but see there is one blue highlighted portion. So here the two plotted series require different axes. So the x-axis of the sine wave is your time in seconds. Okay, and okay, before going to that, let me show you what is the problem here. Okay, so here the plot does not convey much useful information. I mean, which plotting belong to which plot actually? Is this the first plot or is this the second plot? Okay, so here the two axes have been automatically scaled to fit the larger F50 result values, making the sine wave in the blue. So it's kind of difficult to differentiate between the two plots. So how can we solve this problem then? So to solve this problem, what we can do, we have to make certain changes to our program. Okay, so let's make some changes first. Before making the changes, I need two figures actually. Okay, need all in caps. So figure 1, uh, then figure 2, the value 2. I'm going to use this two unique identifiers of each figure. So let me make a comment. Unique identifiers for each figure. Okay, done with this. Now the next change I want to make, we want the T1, we want the wave F50 result and T2. Now here I'm going to create the plot using these two plots. I'm going to differentiate the two plots in two different pictures or figures here. So PLT dot, the first figure that I want is my first figure 1. Oh, did I mistake? Figure 1. Then I want the T1 and wave in the plot. Now we want the axis to be plotted with clarity. So plt.x level, I'll be using one name as time in seconds. Mm, double quotation mark. And plt dot y label. Here I want a name, amplitude in the y-axis in my plot. Okay, then we want another one, axis function. Um, its starting point, then the ending point for x-axis, y-axis, minus 1.2 and 1.2 suppose. So these are the parameters I'll be using in the axis. Okay, this is the first plot. We're done with the first plot. Let's do the same thing again for our next figure as well. Figure 2. I'll be using this plotting as I had it earlier. plt.x label again. The name I'll want to assign it to frequency in Hz for Hertz. Double quotation marks. This is the name. Should be good to go with this. I think so. Let's see. It's working or not. Magnitude. Okay, y label. Then we should be dealing with this kind of axis values right now. Okay, so I need two parameters for starting and ending point of the x and y axis for this plotting minus, let's make it minus 6 plus 6. Then for y, 0 and let's make it 260. Should work actually. Let's see. Okay. So here, I think I did it correctly. Yeah. Okay. So now I have two figures here. So let me just minimize this and let's review the figure 1. Okay. So here, see the two plotted series that we have. Okay, first plot and the second plot in two figures. They require different axes. So the x-axis of the sine wave is our time in seconds, and the x-axis of the FFT result is the frequency in hertz. So the figure function here and here, they can be used to create multiple figures. So each figure corresponds to a window frame to be opened by Matplotlib, and each figure can also contain a plot that uses different axes. Those are the details about these two plottings and the statements I just added to my code right now. Here, the figure function sets the current figure using the argument to identify the figure to activate. So the subsequent calls like plt.plot here and plt.x level affect the current figure. The first figure is created here that you are viewing right now by the matplotlib library automatically calling the statement, this function here. So the call to figure 2 is needed to create a new figure for FFT plot as well, and this axis function is used to set the range of x and y axis. So the single least argument specifies the minimum maximum value of each axis. So here is the mean x value, max x value, mean y value, max y value for the x and y axis. And above the here in the pictures, the axis of the signal frequency plot are set to show only the interesting region of the plot. So in the figure one, we have the first plotting with the time in seconds in the x-axis label and y label as amplitude. And see, -1, -6 is the minimum maximum value of the plotting. And these two parameters are used for the minimum and maximum value in the y-axis. I'm just going to close this and let's review our figure 2. Here, yeah, so I did -6 plus 6 for the starting and ending point, the mean and max value for the x-axis, and these two are the mean and max value for the y-axis. So in this way, we can see two properly plotted uh, plotting figures in two different figures, but in our single code. So it's kind of eased the visibility of the plottings in a proper specified way. Um, while as in the last picture, without having last plotting, without having all these statements inside it, we had the plotting in a clumsier, in a more critical way, where two plots haven't been differentiated or visible proper in one plotting.